In section 2.6, we're going to be talking about graphs of basic functions. And one thing that's in this section that you should be aware of is the concept of continuity. Now, this is something you'll learn more about if you ever have to take calculus. But what continuity means is that the graph can be drawn without picking up your pencil or your pen. You should always do math in pencil, though. And there's different types of continuity, or different points of discontinuity. Now, if continuity means you could draw the whole thing without picking up your pencil, that means that there's two instances where you have to pick up your pencil. One is if there's like a point discontinuity, and one is if there is a jump discontinuity. So let me show you what these look like. A graph of a parabola. This graph is continuous. I just drew the whole thing without picking up my pencil. The graph of y is equal to x, where x can't equal 0, looks like this. You can see I had to pick up my pen right here. That's called a point discontinuity, a point of discontinuity. And then one last one, we'll be learning about this later on in today's lesson. This is called a jump discontinuity, and they're pretty cool. Think about it if you had a graph like this. You could see it looks like stairs. And I'm not, of course, I have to pick up my pen to draw that, so that's why it's called a jump discontinuity. So those are our concepts of continuity and discontinuity. The next main topic, and the most important topic in math, is how to factor. The second most important concept in math is how to graph. And what I wanted to do is talk about different types of parent graphs. Now, when we say parent, that means it's purest form. So they're not moved. These are just what the shapes look like. The first type of graph is called a quadratic. And what I'll do is I'll show you what the graph looks like. Then we'll talk about the domain. And next we'll talk about the range of the graph. So a quadratic graph looks like a parabola. And as you can see, you could plug in any x you want. Those arrows are going to go all the way out to the right and to the left. So the domain would be infinite. But as far as the y value, the range, it looks like it starts at 0 and then it goes up for forever. So that's why the range we would write like that. Second graph you should know is something called a square root graph. So y is equal to the square root. Now you can't plug in negatives, right? So if you had the square root of x, you would start at 0, and you could plug in any x value you want, and you would always get a positive answer. So the domain for a square root function would be starting at 0, and then going up until any number, and the range would also start at 0 and go up to any number. Next is the absolute value function. Now sometimes we abbreviate absolute value, just ABS. If you see that in Excel or on your calculator, it means absolute value. And the absolute value function, well, think about it. At 0, it's 0. At 1, it's 1. 2, it's 2. 3, it's 3. -1 is 1, -2 is 2. So you get this V-looking graph. It's different than a parabola. Parabola is rounded at the vertex. Absolute value is a V. We could take the absolute value of any number, so the domain is infinite. But if you see on the graph, the possible y values start at 0 and then go up until infinity. You will never get a negative answer for absolute value. Next is called a cubic function. And a cubic function looks like an indecisive parabola. So it looks like a parabola on the right side, but then on the left side it changes its mind and goes down. So you could actually raise anything to the third power. This is what the graph of y equals x to the third looks like. This is y equals absolute value of x. Maybe I should have written the equations here. And quadratic would be y is equal to x squared. So you could raise anything to the third power, so the domain would be infinite, and you could see that from the graph. Possible y values, well, it goes up and down for forever. And next is called the cubed root function. Around 5. Now this is a graph y is equal to the cubed root of x. It's a little bit tricky to explain. The cubed root of 0 is 0. The cubed root of 8 is 2. The cubed root of -8 is -2. And if you were to pick more points, you would actually see like a sideways cubic function. It's a little awkward to draw. But you could take the cubed root of anything. You could see that because the graph's pointing to the left and to the right. And the y values, the range, would actually be anything as well. And then we have what's called the greatest integer function. Now, the greatest integer function is probably new to a lot of you. This is what the graph looks like. It's y is equal to kind of like an L and then a backwards L. Sometimes people call this the floor function, and you should just generally know what the shape looks like. This has a jump discontinuity. What the greatest integer function means is we want to find the greatest integer not bigger than x. So let's figure this out. Now remember, you can't get bigger than whatever x is. So let's say x is 0. What's the largest integer not greater than 0? Well, 0, right? 0 is not greater than 0. What about if it's 0.5? 0.5. You can't say 1 because 1's bigger than 0.5. So again, 0.5 is 0. 0.9 would also be 0. But then when you get to 1, it jumps up to 1. 1.1 would still be 1. 1.2 would still be 1. 1.9, the greatest integer not bigger than 1.9 is still 1. But then when you get to 2, it jumps up again. And it's going to keep doing this jumping motion. There's a jump discontinuity here. And the way that we represent it gets close to 1 and then becomes 1 is we put an open circle on the right side. Let's talk about the negative numbers. What's the largest integer not bigger than -1? -1, right? What about not bigger than -0.5? Well, 0 is bigger than that, so it's still -1 up until you get to 0, and then it jumps up. So you can see this graph, there's like a pattern behind it, and that's what the greatest integer function looks like. Now, as far as what the domain would be, we could pick any x value you want. You want to use pi, 3.14, the answer would be 3, right? So as far as what the domain could be, you could pick any number you want for x. And then as far as what the range is, well, that's going to be a little bit tricky. You can't have like look, there's like a big jump here, right? And right here. So for the range, you're not going to be expected to know how to do this, but let's just say the range is the set of x values such that x is an integer. That's technically how you would write it. We talked about those symbols. Remember, this just means such that. Z means integer. And this kind of E, you draw it like a C and then you put a line through it, it's Greek. This means element of. So I just had a few things I wanted to talk about here, just a couple graphs, maybe like a little bit special. So a couple graphs. First graph looks like this. What would the graph of f of x is equal to the floor of x plus 1 look like? Well, in coming sections, we're going to learn how to quickly draw graphs. But up until that point, the way that we generally draw graphs is we pick test points and we make a chart and then we connect our dots. So let's do the same thing for this. I'm going to have a column for x, I'm going to have a column for y. Let's go 1, 2, 3, 4. 1, 2, 3, 4. We'll pick test points and let's see what kind of shape we get. Let's start at 0. 0 plus 1 is 1. And what's the greatest integer not bigger than 1? The answer is 1. What about if we had 0.5? Well, we would get 0+, we'd get 0.5 plus 1. And what's the floor of that? It would be 1. Guessing at 1, it would jump up to be 2. And then we would kind of get this pattern going. Once you get a pattern, you could pretty much figure out what the graph looks like, but let's just confirm. What if we had 1? We're going to be taking the floor of 1 plus 1. The floor of 2 is 2. 1.5, we're taking the floor of 2.5, which is still 2. So you can see that's what the graph looks like. If we're going negative, like let's try negative 1, we're going to have the floor of negative 1 plus 1 is 0. So you can see we still have this pattern going, even if we pick negative numbers. It's a little bit tricky to see that, but even if we had like negative 1.5, negative 1.5 plus 1 is negative 0.5. If you round that down, that's still negative 1, which is what the graph looks like. Negative 1.5 is right here, and the y value there is negative 1. Last type of graph I wanted to go over in this section is something called a piecewise function. So we talked about this in a previous section, but I told you we'd talk about it more, and now's the time to talk about it. So when we have a piecewise function, it looks a little bit like this. The way that we graph a piecewise function is we look to see, okay, like where's the x? If we have an x value that's greater than 2, we're going to use x squared to graph it. If we have an x value that's less than or equal to 2, we're going to use this. So let's see what this graph looks like. It's called piecewise because you have pieces. It's not like just strictly one shape. So maybe I'll go up. We're going to have to go up by 5. So maybe I'll go up 6 in every direction. Okay. So what I'm going to do first is I'm going to start with this piece. This piece is saying if x is less than 2 or equal to 2, the y value is going to be negative 2 times x plus 5. So let's say x is 2. If x is 2, the y value is going to be negative 2 times 2 plus 5, which is negative 4 plus 5, or 1. Right here. If we were to plug 3 in, negative 6 plus 5 is negative 1. If we were to plug 4 in, oh, actually, I'm sorry. we're going values less than 2, right? My mistake. So less than 2, we could plug in 1, right? So if we plug in 1, negative 2 times 1 is negative 2, plus 5 is 3. We go 0, 0 plus 5 is 5. And if we connect these dots, any value less than 2, that would be a linear function, and it will look like that. And that only happens for values less than 2. Now values greater than 2, maybe I'll use green for that. Like let's try 3. 3 squared is 9, right? So 6, 7, 8, 9. 3 is 9. What about like 2.5, right? So it's not going to be x squared at 2, but any number past 2. So whenever you're graphing a piecewise function, let's graph the boundary 2, but we're going to put an open circle there because it's not including 2. That's the one above it. But we put an open circle at 2 just to show that that's the boundary. 2 squared is 4. We're going to put an open circle there. And imagine this. The graph of y equals x squared looks like a parabola. Like that. But it's only going to look like a parabola from values greater than 2. So that's what the graph would look like. And this would be a little bit more like arced. Imagine something like that. And that's going to go up for forever because that's what a parabola looks like. I hope this makes sense. Stay tuned for the next lesson.